Okay, so now we're going to talk about derivatives at a point and some other calculus functions that we're going to need to know for AP Physics C. Um, as we've stated, the derivative is the slope of a graph and any specific point. And if this, for example, were a position graph, then the tangent line would give me the velocity. But I have a different tangent line or a different velocity at different points in time. So if I wanted to find the velocity at, let's say, 2 seconds here, I would plug 2 into my derivative function, and then it would spit out a numerical velocity value. If I wanted to find the velocity over here, let's say time 4, then I would plug in 4 into my function, and it would give me a different velocity numerical value. So this is just finding derivatives at a point. They will give you the variable in which you need to plug in most of the time, and then you just plug and chug into your derivative equation. Okay, higher order derivatives, especially with kinematics, we are going to go into not just the first derivative, but the second derivative. And so, um, yes, we can take derivatives of a derivative. That's what we call a second derivative. We will not get into third derivatives or fourth derivatives, but they are things that are used in higher level science that will allow you to pull out even more information out of a function or a graph. So the notation for a second derivative, actually, for kinematics, we do use the tick marks to talk about second derivatives, or we can just call the second derivative of position A, which is acceleration. Um, and so you will see this notation pop up in E&M. And this is another way to represent the second derivative. Again, the y variable represents the function, and then the x variable in the denominator represents the variable that is changing. So it looks weird and it looks like it's a function with some exponents in it, but it is not an exponent. We show the second derivative as d2y over dx2. Okay, so just a little information on where we use higher order derivatives. The fifth derivative is helpful for DNA analysis, which is kind of cool, population modeling, but that's not stuff we're going to cover in our class. Okay, trig functions we will cover, and we're not going to cover all of them. So the two that we cover are sine and cosine, and those are the two that are in your equation sheet. Here is your power rule, and we're going to get into e to the power and ln later, but we are now talking about our trig functions. So very easy. The derivative of sine is cosine, and the derivative of cosine is negative sine. I never remember when I'm supposed to put a negative in, but I always know where to find it in my equation sheet, just in case I forget. And the equation sheet shows you that if you have a function within your trig function, all you have to do is multiply that function out in front. So if I were to take the derivative of cosine 5t, I would end up getting negative sine, but I also have to multiply the um, derivative of this 5t, which is 5, out in front. So in the end, I get negative 5 sine 5t. The next most common functions we work with in AP Physics C is taking the derivatives of e to the x and ln x. And they have really unique properties to them. They are in your equation sheet and they're pretty simple. The derivative of e to the x is just e to the x, and the derivative of ln x is 1 over x. So the unique thing about these properties, and again, I'm showing you in the equation sheet what you'll have available to you, is that if e has a function within its exponent, then you would multiply that function out in front. And it's very similar to the power rule, so it's pretty simple to memorize. But the ln function is different. If you have a constant in your ln function, or your natural log function, which is represented here, that constant is not multiplied out in front, which is what many students tend to think. So we don't see this that often, but it's an important note to make that the derivative of a natural log function, regardless of how complex the function within that natural log function is, it's always going to be 1 over x, or 1 over the variable. So for this first practice problem, we are going to take the derivative of an exponent function, and our exponent function is 5e to the x. I'm going to give you a minute to do it. You can pause this video, and then we'll go over the answer. So the answer to this one is, C. So if you have a function e to the x, the derivative is just e to the x. We didn't have any complex exponent here, so it's just 5e to the x. It's the same thing. The next one, ln x, also c, that's 1 over x, which is literally in your equation sheet. And then here we've got a complex exponent function, 3e to the 2x. Go ahead and take a second to figure that out. Pause the video if you have to. This one would be 6e to the 2x. So again, the exponent e to the 2x doesn't change, but because it had a variable in front of the, or because it had a multiplier in front of the x function, we took the 2 and multiplied it out in front. Okay, differentials. So differentials are when you're just trying to solve for dy. In every derivative problem, we always solved it as dy over dx, trying to find the derivative function of y with respect to a changing variable x. Now, this isn't much different. All it is solving for dy and moving the changing variable dx as part of the dy function. So let's look at examples to kind of make this a little bit clearer. If I have a y function and I want the derivative of it, I know that the changing variable is x. So I am going to take the derivative with respect to x, which is this right here. So I'm going to multiply the 4 in front, decrease the power. Same with the 2. I multiply that in front, decrease the power. And when I have a constant, the derivative is 0. Now this is my dy dx, the derivative of a y with respect to x. If I'm just trying to solve for dy, then the dx becomes part of the dy function. It gets pulled to the other side. So this is what we call a differential, and you're going to understand a little bit more why we do this extra step when we start talking about integrals. So again, nothing very new here. You're just going to take the derivative, and if they want a differential, just move that dx on the other side